In the nucleus of an atom, protons are positively charged particles, and according to the basic principles of electrostatics, like charges repel each other. Therefore, one might wonder, how do these positively charged protons stay together in such a confined space within the nucleus when they should be repelling each other due to their similar charges? This question is central to understanding the stability of atomic nuclei and leads to a deeper exploration of forces at work inside the nucleus. Here's a detailed explanation. 1. The role of the electrostatic Coulomb force. Protons, being positively charged, experience an electrostatic repulsion. This repulsive force is governed by Coulomb's law, which states that like charges repel each other with a force that is inversely proportional to the square of the distance between them. In a small, densely packed nucleus, the protons are very close together, so the Coulomb repulsion between them is extremely strong. Left unchecked, this repulsive force should cause the protons to fly apart, making it impossible for the nucleus to stay intact. However, we know that most atomic nuclei are stable, so there must be another force counteracting this repulsion. The strong nuclear force. The key to the stability of the nucleus lies in a much stronger force than the electrostatic force, the strong nuclear force, also called the strong interaction. This force is one of the four fundamental forces of nature and is responsible for holding the nucleus together. The strong nuclear force acts between nucleons, which include protons and neutrons. Unlike the Coulomb force, which acts over long distances, the strong nuclear force is a short-range force, meaning it is only effective at distances on the order of a few femtometers. 1 femtometer equals 10 to 15 meters, which is approximately the size of the nucleus. This force is attractive and is incredibly powerful at short ranges, much stronger than the repulsive electrostatic force between protons. It binds the nucleons together, overcoming the Coulomb repulsion at the small distances typical inside the nucleus. Neutrons as a stabilizing factor. Neutrons, which are electrically neutral particles, play a crucial role in stabilizing the nucleus. They experience the strong nuclear force just like protons do, but do not contribute to the repulsive electrostatic forces because they have no charge. Neutrons help to dilute the repulsive forces between protons by adding to the binding force without adding to the repulsion. The presence of neutrons in the nucleus provides a kind of cushioning effect, allowing the strong nuclear force to hold the protons together more effectively. This is why nuclei with more protons, such as heavier elements, require more neutrons to remain stable. If there are too few neutrons, the proton's repulsive forces may overcome the strong nuclear force, causing the nucleus to become unstable and possibly undergo radioactive decay. Why doesn't the strong force act everywhere? You might wonder, if the strong nuclear force is so powerful, why doesn't it cause everything to collapse into a dense mass of protons and neutrons? The reason is that the strong nuclear force has a very limited range. Once the nucleons are separated by more than a few femtometers, the strong force rapidly decreases in strength and becomes negligible. This short range confines the strong force to the size of atomic nuclei, preventing it from affecting particles at greater distances. Quantum effects and exchange particles. The strong nuclear force is explained in more detail by quantum chromodynamics (QCD), the theory that describes the interactions between subatomic particles known as quarks and gluons. Protons and neutrons are made up of smaller particles called quarks, which are held together by the exchange of gluons. Gluons are the force carriers for the strong interaction, similar to how photons mediate the electromagnetic force. In this sense, the strong nuclear force between protons and neutrons can be viewed as a residual effect of the more fundamental force between quarks. This residual strong force is what binds protons and neutrons together within the nucleus. Summary of how protons stay together. To summarize, protons stay together in the nucleus because of the balance between two competing forces. Electrostatic repulsion. This is the repulsive force between the positively charged protons, which, by itself, would push the protons apart. Strong nuclear force. This is a powerful attractive force that acts between nucleons, protons, and neutrons over very short distances. It is much stronger than the repulsive Coulomb force, but only works within the confined space of the nucleus. Neutrons help to stabilize the nucleus by contributing to the strong force without adding any extra repulsive charge. Therefore, even though protons have the same positive charge and should repel each other, the strong nuclear force is strong enough to hold them together in the nucleus, maintaining the stability of atoms. This delicate balance between the strong nuclear force and the repulsive Coulomb force is what makes atomic nuclei possible and is a fundamental aspect of how matter is structured in the universe.